Light physics. Understanding the particle wave duality of electromagnetic radiation light is fundamental to understanding quantum theory and other phenomena as well as the nature of light. One of the biggest scientific developments in the previous century was the discovery that very small objects did not obey the same rules as everyday objects. What are electromagnetic waves? In plain terms, electromagnetic waves are simply known as light. Through the term light is sometimes used to specify visible light that which can be detected by the eye, and other times is used more generally to refer to all forms of electromagnetic radiation. To fully understand electromagnetic waves, it is important to understand the notion of a field and the relationship between electricity and magnetism. This will be explained in more detail in the next section, but in essence, electromagnetic waves, light waves, consist of an electric field wave oscillating in a plane perpendicular at right angles to a magnetic field wave. If electromagnetic radiation acts as a wave, then any particular electromagnetic wave will have a frequency and wavelength associated with it. The frequency is the number of oscillations per second, measured in hertz, where 1 hertz is equal to 1 by second, 1 per second. The wave length is the distance between wave crests. The product of the frequency and wavelength gives the wave speed, which for light in a vacuum is approximately 3 into 10 8 minutes second. Unlike most waves such as sound waves, for example, electromagnetic waves do not require a medium through which to propagate and hence can traverse the vacuum of empty space which they do at the speed of light, the fastest speed in the universe. Fields and electromagnetism. A field can be thought of as an invisible array of vectors, one at each point in space, indicating the relative magnitude and direction of a force an object would feel if placed at that point. For example, a gravitational field near the surface of the earth would consist of a vector at each point in space pointing directly toward the center of the earth at the same altitude or altitude. All of these vectors would have the same magnitude. If a mass were to be placed at a given point, then the gravitational force it feels would depend on its mass and the value of the field there. Electric fields and magnetic fields work the same way, except they apply forces depending on an object's charge and magnetic moment respectively instead of its mass. The electric field results directly from the existence of charges, just as the gravitational field results directly from mass. The source of magnetism, however, is from moving charges or equivalently changing electric fields. In the 1816 second physicist James Clerk Maxwell developed a set of four equations that completely describe the relationship between electricity and magnetism. This equation basically showed how electric fields are generated by charges, how no fundamental magnetic monopoles exist, how changing magnetic fields can be generated an electric field, and how current or changing electric fields can generate magnetic fields. Shortly after the derivation of this equation, a solution was found describe a self-propagating electromagnetic wave. This wave was predicted predicted to move to the at the speed of light, and indeed turned out to actually be light. The electromagnetic spectrum. Electromagnetic waves can come in many different wavelengths and frequencies so long as the product of the wavelength and frequency of a given wave equals c. The speed of light. The forms of electromagnetic radiation include from longer wavelengths or low energy to shorter wavelengths or high energy. Radio waves 0.187 to 60, microwaves 1 mm to 187 mm, infrared wave 750 nm is or to 1 mm, visible light 400 nm to 750 nm. These wavelengths are detectable by the human eye and often subdivided into a visible spectrum. Ultraviolet light 10 nm to 400 nm, X-rays 10-12 m to 10 nm, gamma rays greater than 10-12 m. What are photons? Photons are the name of quantized light particles of electromagnetic radiation. Albert Einstein introduced the notion of light quanta photons in an early 20th century paper. Photons are massless and they do not obey number conservation laws, meaning they can be created and destroyed. They do, however, obey energy conservation. In fact, photons are considered to be in a class of particles that are force carriers. The photon is the mediator of the electromagnetic force and acts as a packet of energy that can be transferred from one place to another. You are probably thinking that it's rather strange to suddenly be speaking of electromagnetic waves as particles, since waves and particles seem like two fundamentally different constructs. And indeed, it's just this sort of things that makes the physics of the very small so strange. In the next few sections, the notions of quantization and particle wave duality are discussed in more detail. How are electromagnetic waves or photons produced? Electromagnetic waves result from oscillation in electric and magnetic fields. If a charge moves back and forth along a wire, it creates a changing electric field, which in turn creates a changing magnetic field, which then self-propagates. Atoms and molecules which contain moving charges in the form of electron clouds are able to interact with electromagnetic radiation in interesting ways. In an atom, the electrons are only allowed to exist in very specific quantized energy states. If an electron wants to be in a lower in energy state, it can do so by emitting a discrete packet of electromagnetic radiation to carry off the energy. Conversely, in order to jump into another energy state, that same electron must absorb a very specific discrete packet of energy as well. The energy associated with an electromagnetic wave depends on the wave's frequency. As such, atoms can absorb and emit only very specific frequencies of electromagnetic radiation consistent with their associated quantized energy levels. These energy packs are called photons. What is quantization? Quantization refers to something being restricted to discrete bulbs versus a continuous spectrum. When atoms absorb or emit a single photon, they do so at only very specific quantized energy values described by quantum mechanics. This single photon can really be thought of as a discrete wave packet. An amount of energy can only be emitted in multiples of an elementary unit. Planck's constant is the equation that relates the energy E of a photon to its frequency is equal to S into V, where V the Greek letter nu is the photon's frequency and Planck's constant S is equal to 6.62607015 into 10 inverse 34 J wave particle duality. You will hear people use the words photon and electromagnetic radiation interchangeable, even though that it seems like they are different things. When speaking of photons, people are typically talking about the particle properties of this phenomenon, whereas when they are talking about electromagnetic waves or radiation, they are speaking to the wave-like properties. Bohr model definition and development. In the early 20th century, Danish physicist Niels Bohr made many contributions to atomic theory and quantum physics. Among these are his model of the atom, which was an improved version of the previous atomic model by Ernest Rutherford. This is officially known as the Rutherford-Bohr model, but is often called the Bohr model for short. Number one, electrons are able to move in certain discrete stable orbit without radiating energy. Number two, these special orbits have angular momentum values that are integer multiples of the reduced Planck's constant is sometimes called S bar. Number three, the electrons can only gain or lose very specific amounts of energy by jumping from one orbit to another in discrete steps, absorbing or emitting radiation of a specific frequency. Bohr model in quantum mechanics. Bohr model provides a good first-order approximation of energy levels for simple atoms such as the hydrogen atom. And electron angular momentum must be L is equal to mv, r is equal to ns, where m is the mass of the electron, v is its velocity, r is the radius and which it orbits the nucleus, and quantum number n is a non-zero integer. Since the lowest value of n is 1, this gives the lowest possible value of the orbital radius. This is known as the Bohr radius and it is approximately 0.0529 nanometers. An electron can be no closer to the nucleus than the Bohr radius and still be in a stable orbit. Each value of n provides a definite energy at a definite radius known as an energy shell or energy level. In these orbits, the electron does not radiate energy and so does not fall into the nucleus. Bohr model is consistent with observations leading to quantum theories such as Einstein's electric effect, matter wave, and the existence of photons. Although Bohr did not believe in the existence of